Tonight, as you settle into comfort and let your breathing slow, I want to take you on a gentle journey outward, beyond the familiar planets of our solar system, beyond the reach of any spacecraft we have ever built, to worlds that orbit distant suns scattered across the darkness of space. These worlds are called exoplanets, and they circle stars so far away that their light takes years, sometimes centuries, sometimes thousands of years to reach your eyes. An exoplanet is simply a planet that orbits a star other than our sun. The word comes from extrasolar planet, meaning a planet outside our solar system, beyond the gravitational embrace of the star we know best. For most of human history, we could only wonder if such worlds existed. Ancient philosophers gazed up at the stars and imagined that those distant points of light might have their own families of planets, their own cosmic architectures spinning silently in the void. But wondering and knowing are different things, and for thousands of years, we had no way to bridge that gap. The stars were too far away, the planets too small and dim, hidden in the overwhelming glare of their parent suns. You can picture it this way. Imagine trying to see a firefly hovering next to a brilliant searchlight, but the searchlight is not across a field or across a city. It is thousands of miles away, so far that the searchlight itself appears as nothing more than a faint glimmer. The firefly, already tiny, already dim, disappears completely in that distant brilliance. That is the challenge astronomers faced when they first tried to find planets around other stars. The planets were the fireflies, lost in the blazing light of distant suns. For a long time, many scientists believed that planets must exist around other stars. It seemed natural, almost inevitable. Our sun had planets. Why would our star be special? Why would we be the only system with worlds orbiting through space? The universe appeared to be built on patterns, on repeated structures, on themes that played out across vast scales. Gravity pulled gas and dust together into stars. It seemed reasonable that the leftover material would clump and spin and form planets, just as it had done here in our solar system. But reasonable assumptions are not the same as proof, and science requires evidence, requires observation, requires the patient work of looking and measuring and confirming. So astronomers waited and watched and developed new tools, more sensitive instruments, cleverer methods for teasing tiny signals out of the noise of the cosmos. The breakthrough came in the 1990s, a time not so long ago, within the lifetime of many people alive today. In 1995, two Swiss astronomers, Michel Mayer and Didier Queloz, announced something extraordinary. They had found a planet orbiting a sun-like star called 51 Pegasi, located about 50 light-years from Earth. That means the light you see from that star tonight left its surface 50 years ago, traveled through the endless dark, and finally arrived at your eyes carrying the faint signature of a world. This first exoplanet was strange, nothing like the planets in our solar system. It was enormous, at least half the mass of Jupiter, our largest planet, but it orbited incredibly close to its star, much closer than Mercury orbits our sun. It completed one full orbit, one full year, in just over 4 Earth days. Astronomers called it a hot Jupiter, a giant planet scorched by the radiation of its nearby star, a type of world we had never imagined before. The discovery of 51 Pegasi b, as the planet was named, changed everything. It opened a door that had been closed for all of human history. Within months, other teams announced more exoplanet discoveries. Within years, dozens were known. Within 2 decades, thousands. Each discovery added another point of light to our growing map of worlds beyond our sun. What makes this discovery so calming, so beautiful in its implications, is how it expanded our sense of home. For all of recorded history, humanity knew of exactly 8 planets, the worlds that circle our sun: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. That was the full catalog of planets in the universe as far as we knew. 8 worlds, 1 star, 1 small family hanging together in space. Now, as you rest here, as your muscles release their tension and your mind begins to drift, you live in a universe where we know of more than 5,000 confirmed exoplanets, with thousands more candidates waiting to be verified. 5,000 worlds, each one a place, a sphere of rock or gas hanging in space around another sun. The number grows every month, every year, as our telescopes find more and more of these distant companions. Let that sink in gently. 5,000 known worlds beyond our solar system. 5,000 places where alien skies stretch overhead, where unfamiliar stars pattern the darkness, where days and nights unfold according to different rhythms, different orbital dances, different laws of light and shadow. These planets orbit stars of many different types. Some circle red dwarfs, stars much smaller and cooler than our sun, stars that glow with a dim orange light and can burn steadily for trillions of years, far longer than the current age of the universe. Other exoplanets orbit stars similar to our sun, yellow dwarf stars of medium size and temperature, stars in their long stable middle age, pouring steady light into space. Still others circle massive blue giants or orbit in binary star systems where two suns wheel around each other, creating complex patterns of light and gravity. The distances involved are almost impossible to grasp in any visceral way, but we can try to feel them gently, to let them wash over us like a slow tide. The nearest known exoplanet orbits Proxima Centauri. The closest star to our sun, Proxima Centauri, sits about 4.2 light years away. That means if you could travel at the speed of light, the fastest speed possible in our universe, it would take you 4.2 years to reach it. Light itself, racing through space at 186,000 miles every second, takes more than 4 years to cross that gap. In more familiar units, Proxima Centauri is roughly 25 trillion miles away. 25 followed by 12 zeros, a number so large it loses meaning, becomes just a sound, just a rhythm. 25 trillion miles. You could drive a car for billions of years and never arrive. You could walk for trillions of years. The distance swallows human scales of measurement, reduces them to whispers. And that is the nearest exoplanet, the closest world beyond our sun. Most of the exoplanets we have discovered lie hundreds or thousands of light years distant. Their light left them before you were born, before your parents were born, before recorded history began. You are seeing them not as they are now, but as they were when their light began its long journey toward Earth. There is something deeply peaceful about this, about the way the universe reveals itself to us across time, across distance, across the patient passage of photons through empty space. These worlds exist out there right now, at this very moment, but we see them as they were, frozen in the past by the speed of light. It is like looking at old photographs, except the photographs are alive, still happening, just very far away. The methods we use to find these distant worlds are clever and indirect. We cannot usually see exoplanets directly. They are too faint, too overwhelmed by the light of their stars. Instead, we watch the stars themselves and look for tiny changes, subtle variations that hint at the presence of an unseen companion. One method, called the transit method, relies on patient observation of a star's brightness. If a planet passes in front of its star from our point of view, it blocks a tiny fraction of the star's light. The star appears to dim slightly, then return to normal brightness once the planet has moved on. By watching thousands of stars and waiting for these miniature eclipses, astronomers can identify planets and even measure their size based on how much light they block. Imagine standing in a field at night, watching a distant lighthouse beam sweep across the darkness. Now imagine a moth crosses in front of that lighthouse, so far away you can barely see the light itself. The moth blocks an infinitesimal amount of the beam, causes the tiniest flicker. That is what astronomers are detecting when they find planets using the transit method, a brief dimming, a momentary shadow, repeated every time the planet completes an orbit and passes in front of its star again. Another method watches the star's motion, looking for a subtle wobble. Planets do not actually orbit their stars in a simple way. Instead, both planet and star orbit their common center of mass, the balance point between them. For a massive planet orbiting close to its star, this wobble becomes detectable. The star shifts slightly toward us, then away from us, then toward us again, pulled by the gravity of its unseen companion. This motion changes the color of the star's light ever so slightly, shifting it toward the blue when the star moves toward us, toward the red when it moves away. By measuring these tiny color shifts, astronomers can infer the presence of a planet and even estimate its mass. These are indirect methods, shadow techniques, ways of seeing without directly looking. But they work. They have revealed thousands of worlds, pulled them from hiding, given us proof that planets are not rare exceptions but common features of the galaxy, scattered around most stars like seeds around trees in a vast forest. Before 1995, we knew of 0 planets beyond our solar system. We suspected they existed, hoped they existed, built our theories assuming they existed, but we had no proof, no examples, no confirmed detections. In just 30 years, that emptiness has filled with thousands of known worlds. We went from wondering if planets existed around other stars to knowing that they are everywhere, that the galaxy is rich with them, that almost every point of light in the night sky likely has its own retinue of orbiting spheres. This knowledge changes something fundamental about our place in the cosmos. We are not alone in having a world. Earth is one planet among multitudes, one small sphere in an ocean of spheres, each one spinning through space in its own way, each one shaped by its own history of formation and evolution. Some of these worlds are probably barren rocks, airless and cold, pockmarked by ancient impacts, geologically dead for billions of years. Others might have thick atmospheres, crushing pressures, violent weather systems that rage across their surfaces without pause. Some might be covered entirely by deep oceans, water worlds with no dry land, just endless seas beneath alien skies. Others could have vast deserts, frozen tundras, volcanic landscapes, or terrains we have never imagined, combinations of chemistry and physics that produce environments completely unlike anything in our solar system. As you rest here, breathing slowly, letting your body sink deeper into relaxation, you can picture one of these distant worlds. Choose any star you like, any point of light you remember seeing in the night sky. There is likely a planet there, perhaps several planets, perhaps a whole system of worlds orbiting in nested rings around that distant sun. Those worlds exist right now, even as you cannot see them, even as their light mingles with the light of their star and disappears in the glare. On some of those worlds, it is day, the local sun hanging high in the sky, warming rock or water or ice, casting shadows that lengthen and shift as the planet rotates. On others, it is night, and the darkness is profound, broken only by the light of neighboring planets, distant moons, or the faint glow of the galaxy itself stretching across the sky like a river of light. The discovery of exoplanets is still unfolding. New planets are announced regularly, added to our growing catalog of known worlds. Each discovery is a small victory, another piece of the puzzle clicking into place, another thread in the tapestry of worlds that fills our galaxy. Some discoveries excite astronomers more than others, the ones that suggest Earth-like conditions, the ones that orbit in the habitable zone where liquid water could exist on a planet's surface, the ones that might, just might, harbor some form of life. But every exoplanet is remarkable simply for existing, for being a place, a location in space where matter has gathered and organized itself into a spherical world, where gravity holds sway, where physics plays out its endless equations, where time passes and things happen even if no one is there to watch. The universe is larger than we ever imagined, more full of wonders, more generous with its creativity. Before we found the first exoplanet, we could speculate about alien worlds, but we could not point to them, could not say with certainty that they were real. Now we can. Now we know that worlds beyond our sun are not fantasies or wishful thinking. They are actual places, physical objects, confirmed by observation, measured by science, added to the list of real things that exist in the cosmos. This knowledge is a gift, a gentle expansion of what is possible, what is real, what shares the universe with us. As you drift towards sleep, as your thoughts become looser and less defined, let this truth settle into your awareness. The galaxy is full of planets. Worlds orbit almost every star. We are surrounded by spheres of rock and gas, spinning in the darkness, each one a small miracle of gravity and time. The search for exoplanets continues, patient and methodical, adding new discoveries month after month, year after year. Telescopes stare at patches of sky, watching for the telltale dimming of starlight, measuring the wobble of distant suns, building our census of worlds one planet at a time. And with each new addition, our picture of the universe becomes richer, more textured, more filled with places where matter has arranged itself into the familiar shape of a planet, a sphere hanging in space, following its ancient orbit around a star. You live in a time when this knowledge is new, when the map of worlds beyond our sun is still being drawn, when surprises await in every observation, every analysis, every careful measurement of distant light. It is a quiet revolution, unfolding not with explosions or drama, but with the steady accumulation of data, the patient work of science revealing what has always been there, waiting to be found. Rest now, and let your mind wander among those distant worlds, those spheres of rock and gas orbiting alien suns, those places that exist in the depths of space, real and physical and numerous beyond counting, spinning through the darkness as they have for billions of years, as they will for billions more, each one a small note in the great symphony of worlds that fills our galaxy, our universe, our home. Now that you know these distant worlds exist, thousands of planets circling thousands of stars, you might wonder how we find them, how we pull them from their hiding places in the vast darkness of space. The methods astronomers use are gentle and indirect, like reading whispers carried on a distant wind, like noticing the smallest ripple crossing a still pond. There is something meditative about these techniques, something that requires patience and careful attention, watching and waiting for subtle signs that most would never notice. Finding an exoplanet is not like spotting a bird in a tree or a ship on the horizon. You cannot simply point a telescope at a star and see the planets orbiting around it, cannot make out their shapes or colors or features. The distances are too great, the planets too small and dim, the light from their stars too overwhelming. It is like trying to see a grain of sand next to a bonfire, except the bonfire is 50 light years away, and the grain of sand catches none of its own light, only reflects the tiniest fraction of the fire's glow. So astronomers had to become clever, had to learn to see without looking directly, to find planets by the traces they leave behind, the small disturbances they create in the fabric of light and gravity that reaches us from distant stars. They developed methods that sound simple in description but require extraordinary precision in practice, technologies that can measure changes so tiny they border on the invisible. The two most successful methods are called the transit method and the radial velocity method, and together they have discovered most of the known exoplanets in our growing catalog. Each method has its own poetry, its own way of revealing hidden truths, and understanding them brings a kind of peace, a sense of how much can be learned from patient observation, from watching carefully and waiting for patterns to emerge. Let us begin with the transit method, perhaps the most intuitive of the techniques, though it requires a very specific alignment, a fortunate geometry that allows us to see what is otherwise invisible. Imagine you are sitting in a quiet room at dusk, watching through your window as the sun sets. The room grows dimmer as the sun sinks toward the horizon, but the change is gradual, smooth, the fading of daylight that happens every evening. Now imagine a bird flies past your window, crossing directly between you and that setting sunday. For just a moment, a fraction of a second, the bird's silhouette blocks a tiny portion of the sun's light. The room dims slightly, almost imperceptibly, then returns to its previous brightness as the bird flies on. That is essentially the transit method. Astronomers point their telescopes at a star and measure its brightness with extreme precision, watching for the tiny dimming that occurs when a planet passes in front of the star from our point of view. The planet itself is invisible, too faint to see against the star's glare, but its shadow, its silhouette, can be detected as a brief dip in the star's light output. The dimming is remarkably small. When Earth passes in front of the sun from the perspective of a distant observer, it blocks only about 1/100% of the sun's light. Jupiter, much larger, blocks about 1%. For a telescope staring at our sun from far away, that would appear as the faintest dip in brightness, a fluctuation that could easily be mistaken for random variation or measurement error. Yet astronomers have learned to detect these minuscule changes, to filter out the noise and identify the genuine signal of a planet crossing its star. The beauty of the transit method lies in its repetition. A planet orbits its star over and over, following the same path through space, and each time it completes an orbit, it passes in front of the star again, creating another brief dimming event. By watching a star for weeks or months or years, astronomers can see this pattern repeat, can measure the exact time between transits and calculate the planet's orbital period, how long it takes to complete one full circle around its sun. The depth of the dimming tells us about the planet's size. A larger planet blocks more light, creates a deeper dip. A smaller planet causes a shallower dip. By measuring how much the star's brightness decreases during a transit, astronomers can calculate the planet's diameter with remarkable precision, can determine whether they are looking at something Earth-sized or Jupiter-sized or somewhere in between. The duration of the transit, how long the dimming lasts, depends on the planet's orbital distance and the size of the star. A planet in a close orbit races across the face of its star quickly, causing a brief dimming that might last only an hour or two. A planet in a wider orbit moves more slowly, takes longer to cross the star's disk, might cause a dimming that lasts for several hours or even days. Picture this happening out in space right now, at this very moment, as you rest here with your eyes closed, breathing slowly. Somewhere among the billions of stars in the galaxy, a planet is passing in front of its sun. The planet itself knows nothing of this, has no awareness of its alignment, simply follows the ancient groove of its orbit as it has for millions or billions of years. The star continues to shine, pouring light into space in all directions, and from one tiny direction, from one specific angle across vast distances, we happen to be watching, and we see the star dim slightly as the planet slides across its face. This alignment, this perfect geometry, only happens for a small fraction of planetary systems. Most planets orbit their stars at angles that never bring them between us and their sun. From our point of view, they pass above or below the star, never crossing its face, never creating a transit. We could watch those stars forever and never see the telltale dimming, even though planets are there, orbiting invisibly, hidden by their unfortunate angle. But the galaxy contains so many stars that even a small fraction represents millions of opportunities. By watching hundreds of thousands of stars simultaneously, astronomers increase their chances of catching those rare alignments, those planetary systems oriented just right for transits to occur. Space telescopes like Kepler and TESS have stared at vast fields of stars, monitoring their brightness day after day, night after night, building up enormous databases of stellar light curves, graphs showing how each star's brightness changes over time. In those light curves, planets appear as small regular dips, repeating with clockwork precision. The pattern stands out against the random fluctuations of stellar activity, the irregular variations caused by star spots or stellar rotation or instrument noise. Once astronomers identify a regular repeating dip, they can confirm it as a planet, add it to the catalog, begin studying its properties in detail. There is something deeply calming about this process, about the idea that we can discover worlds simply by watching starlight with patience and care, by noticing patterns that repeat over time, by paying attention to the smallest changes in brightness that most would never see. It requires no dramatic intervention, no close approach, no physical contact. Just observation, just watching and measuring and waiting for the pattern to reveal itself. The other major method, radial velocity, operates on different principles but with similar patience, similar attention to tiny details that betray the presence of an unseen world. When we say a planet orbits a star, we are simplifying what actually happens. The planet does not really circle a stationary star like a weight on a string. Instead, both planet and star orbit their common center of mass, the balance point between them. For a massive star and a smaller planet, this center of mass lies very close to the star's center, often inside the star itself, but the star still wobbles slightly, shifting back and forth as the planet pulls on it with gravitational force. You can picture this with a simple image. Imagine two dancers holding hands, spinning together. If one dancer is much larger and heavier than the other, the smaller dancer swings in a wide circle while the larger dancer only sways slightly, barely moving, but still responding to the pull of their partner. The star is the large dancer, the planet the small dancer, and gravity is the invisible hand linking them together. This stellar wobble is tiny, impossibly small for distant stars, but it can be detected through a clever trick involving the Doppler effect, the same principle that changes the pitch of a siren as an ambulance races past you on the street. When a star moves toward us, even very slightly, the light waves it emits get compressed, shifted toward shorter wavelengths, toward the blue end of the spectrum. When the star moves away from us, the light waves stretch out, shift toward longer wavelengths, toward the red end of the spectrum. As a planet orbits and pulls its star into this gentle back and forth motion, the star's light shifts from slightly blue to slightly red and back again, over and over, with a period that matches the planet's orbital period. The shifts are minuscule, far too small to see with your eyes, impossible to detect without sophisticated instruments called spectrographs that can split starlight into its component wavelengths and measure them with extreme precision. A star wobbling because of an orbiting planet might move toward and away from us at speeds of just a few meters per second, walking pace, bicycle pace, slower than a car in a parking lot. Detecting this requires measuring the wavelength of starlight with an accuracy of 1 part in a billion or better, like measuring the distance across a football field to within the width of a single atom. Yet astronomers can do this. They have built instruments sensitive enough to detect these tiny wobbles, to watch stars sway back and forth as their planets orbit, to infer the presence of worlds they cannot see directly from the rhythmic motion of the stars themselves. The radial velocity method tells us different things than the transit method. It reveals the planet's mass, or at least a minimum mass, because the amount of wobble depends on how massive the planet is and how close it orbits. A massive planet in a close orbit creates a strong, fast wobble. A smaller planet farther away creates a weaker, slower wobble. By measuring the amplitude and period of the stellar motion, astronomers can calculate the planet's orbital period and estimate its mass. The first confirmed exoplanet, 51 Pegasi b, was discovered using the radial velocity method. Michel Mayor and Didier Queloz measured the wobble of the star 51 Pegasi and found it moving back and forth with a period of about 4 days, betraying the presence of a massive planet in an extremely close orbit. That discovery opened the floodgates, showed that the method worked, that planets could be found by listening to the subtle song of stellar motion recorded in light. Radial velocity has one limitation compared to the transit method. It only measures the component of the star's motion that is toward or away from us, the motion along our line of sight. If a planet's orbit is tilted so that the star moves mostly side to side from our perspective, we miss most of the wobble, can only detect a small fraction of the motion. This means radial velocity tends to underestimate planet masses unless we know the exact tilt of the orbit, which we usually do not. But when we can observe a planet with both methods, when a transiting planet also causes a measurable radial velocity wobble, we gain a complete picture. The transit tells us the planet's size, the radial velocity tells us its mass, and together they allow us to calculate the planet's density, to determine whether we are looking at a gaseous giant like Jupiter, a rocky world like Earth, or something entirely different. As you lie here, feeling the weight of your body against the surface beneath you, breathing in and out in a slow rhythm, you can imagine astronomers doing this work right now, tonight, on the other side of the world where telescopes are open to the dark sky. They are collecting starlight, splitting it into spectra, measuring tiny shifts in wavelength, watching for the repeating pattern that indicates an orbiting planet. Or they are monitoring the brightness of thousands of stars, waiting for the characteristic dip that means a transit is occurring, another world passing in front of another distant sun. These methods require time, require patience, require watching the same stars again and again, building up data, confirming patterns, eliminating false positives. A single transit proves nothing. It could be an instrumental glitch, a background star, an asteroid, anything. But 3 transits with the same period start to look convincing. 5 transits become strong evidence. 10 transits are confirmation. The planet is real, its orbit is known, its properties can be measured and recorded. There are other methods too, less common but still valuable, each with its own particular strengths. Direct imaging, where powerful telescopes block the star's light and try to photograph planets directly, has succeeded for a small number of large planets orbiting far from their stars, worlds that glow with infrared heat from their formation. Gravitational microlensing, where a foreground star and its planets bend and magnify the light of a more distant star through their gravity, has revealed planets that would be impossible to detect any other way, including worlds drifting freely through space without any star at all. But the transit method and radial velocity remain the workhorses of exoplanet discovery, the techniques that have found thousands of worlds, that continue to add new planets to our catalog month after month, building our census of the galaxy's planetary population one careful observation at a time. The process is quiet, methodical, almost meditative. There are no explosions, no collisions, no dramatic events. Just starlight falling on sensors, photons collected one by one, patterns emerging from noise, worlds revealing themselves through the tiniest variations in brightness or color, shadows and wobbles that tell of distant spheres moving through space far beyond our reach. In a way, this is the perfect work for quiet contemplation, for the edge of sleep when your mind is open and receptive but not actively striving. You are not asked to solve anything, to figure anything out, only to appreciate the gentle cleverness of these methods, the way they extract information from light that has traveled for years or decades or centuries across empty space, carrying within it the subtle signature of worlds unseen. As your breathing deepens and your thoughts begin to drift, picture one more image, a distant star observed by both methods simultaneously. Every 4 days, the star dims slightly as a planet passes across its face, blocking a fraction of a percent of its light. And at the same time, measured in the fine structure of the star's spectrum, a gentle wobble, the star moving toward us, then away, then toward us again, swaying to the gravitational dance with its planetary companion. From these two simple patterns, these two quiet signals embedded in starlight, we know a world is there. We can calculate its size and mass and density, can determine its orbital period and distance from its star, can begin to imagine what that world might be like, even though we cannot see it directly, even though it remains hidden in the glare of its sun, visible only through the traces it leaves in light, only through the patient art of reading starlight and finding the hidden worlds written there in patterns of shadow and motion, waiting to be discovered by those who know how to look, how to listen, how to wait for the universe to reveal its secrets one careful measurement at a time. Rest now, and let these thoughts fade like stars at dawn, gentle and gradual, leaving behind only the deep peace of knowing that somewhere, right now, starlight is carrying new secrets toward us across the darkness, and patient eyes are watching, and more worlds are waiting to be found. As you continue to relax, as your body settles more deeply into stillness, I want to guide you through the remarkable variety of worlds that we have found orbiting distant stars, the strange and beautiful diversity of planets that fills our galaxy. Before we discovered exoplanets, we only knew the 8 worlds of our solar system, and we assumed that other planetary systems would look much like ours, with small rocky planets close to the star and large gas giants farther out, a neat arrangement that seemed logical and orderly. But the universe had other ideas. The exoplanets we have found are wonderfully strange, delightfully unexpected, a cosmic menagerie of worlds that challenge our assumptions and expand our imagination. There are planets that should not exist according to our old theories, planets in configurations we never predicted, planets with properties that seem impossible until you remember that the universe is vast and creative and full of surprises. Let us begin with the hot Jupiters, because they were among the first exoplanets discovered, and they immediately told us that planetary systems could be very different from our own. A hot Jupiter is a gas giant planet, similar in size and composition to our Jupiter, but orbiting extremely close to its star, much closer than Mercury orbits our Sun. These worlds complete their orbits in just a few days, sometimes even hours, racing around their stars at tremendous speeds, locked in tight gravitational embraces that subject them to intense stellar radiation. Picture a planet as large as Jupiter, a sphere of hydrogen and helium big enough to swallow Earth more than 1,000 times over, but placed so close to its sun that the side facing the star is heated to temperatures of 2,000 or 3,000 degrees. The atmosphere on the day side is not just warm or hot but scorching, hot enough to vaporize rock, hot enough to turn metals into gas. Clouds on these worlds, if they form at all, might be made of silicates or iron droplets, minerals that would be solid rock on Earth but exist as vapor or liquid in the extreme heat of a hot Jupiter's day side. The planet's atmosphere flows from the intensely heated day side to the cooler night side in powerful winds that race around the planet at thousands of miles per hour, trying to redistribute the heat, to balance the extreme temperature difference between the hemisphere that always faces the star and the hemisphere that remains in eternal darkness. Many hot Jupiters are tidally locked, meaning one side permanently faces their sun while the other side faces away into space, creating a world of permanent day and permanent night with a twilight zone in between where the sun hangs forever on the horizon. On the day side of a hot Jupiter, if you could somehow stand on a platform suspended in the upper atmosphere, you would see the star filling a huge portion of the sky, an enormous blazing disk pouring radiation down onto the planet, heating the gas below until it glows. The sky itself would shimmer with heat, would be filled with strange hazes and vapors that shift and flow in the constant wind. Looking up, you would not see stars, not through the thick atmosphere and the overwhelming glare of the nearby sun, just a dome of hot luminous gas stretching overhead, orange or red or yellow depending on the chemistry of the atmosphere. On the night side, the scene would be entirely different. Here in the permanent darkness, the temperature drops, though not as much as you might expect because the fierce winds carry heat from the day side. The night sky would be truly dark, scattered with stars, a view out into the universe unobstructed by any sun. But the darkness would not be calm or peaceful. Those same winds that carry heat also create turbulence, storms that dwarf any weather system on Earth, vortices and jet streams that churn through the atmosphere without pause. Hot Jupiters were unexpected. In our solar system, the gas giants orbit far from the sun, out where it is cold, where ice and gas could accumulate during the early formation of the planets. The conventional theory said that gas giants could only form far from their stars, out beyond what is called the frost line, the distance where water ice can exist. Finding gas giants orbiting closer to their stars than Mercury orbits our sun seemed impossible, a violation of everything we thought we knew. But the universe found a way. Astronomers now believe that hot Jupiters form farther out in their solar systems, beyond the frost line where gas giants should form, and then migrate inward, spiraling slowly toward their stars through interactions with the disk of gas and dust that remains after the star's formation. Over millions of years, these giant planets move from the outer system to the inner system, settling into close orbits where they remain, scorched and strange, for billions of years. Now let your mind drift to a different type of world, the super-Earths, planets that have no equivalent in our solar system, that fill a gap between the rocky terrestrial worlds and the gas giants. A super-Earth is a planet larger than Earth but smaller than Neptune, typically anywhere from 1.5 to 10 times Earth's mass. These worlds are among the most common types of exoplanets we have found, yet our solar system has none of them, nothing between Earth at 1 Earth mass and Neptune at 17 Earth masses. It is a curious absence, a missing category in our home system that appears abundantly elsewhere. Super-Earths come in many varieties. Some are rocky worlds, scaled-up versions of Earth with thicker crusts, more powerful gravity, possibly more volcanic activity driven by their greater internal heat. On such a world, if it orbits in the habitable zone at the right distance from its star, you might find continents and oceans, mountains and valleys, weather systems and seasons, all the familiar features of a terrestrial planet but on a larger scale, under a heavier gravitational pull that would make everything feel denser, more solid, harder to lift. Walking on a super-Earth with twice our planet's mass would feel strange. Your weight would increase, your muscles would strain against the stronger gravity, each step would require more effort. But the landscape might look hauntingly familiar, rock and soil and perhaps water, a planet that resembles home but with everything amplified, the mountains taller because the planet is bigger, the oceans deeper because there is more surface area to fill, the atmosphere thicker because the stronger gravity can hold more gas. Other super-Earths might be mini Neptunes, worlds with thick atmospheres of hydrogen and helium surrounding a rocky or icy core. These planets blur the line between rocky and gaseous, between terrestrial and giant. They are too large and light to be purely rocky, but too small and dense to be gas giants like Jupiter. Their atmospheres might extend thousands of miles above their surfaces, gradually transitioning from a dense lower layer that might be liquid or supercritical fluid down to a solid core of rock and ice at the center. On a mini Neptune, there might be no clear surface to stand on, no boundary between atmosphere and solid ground, just layers of increasing density and pressure as you descend, gas giving way to liquid giving way to exotic forms of ice compressed by the weight of the atmosphere above. The upper atmosphere might be clear, allowing light from the star to penetrate deep into the layers below, or it might be shrouded in hazes and clouds of methane or ammonia or water vapor, depending on the planet's temperature and distance from its sun. Some mini Neptunes orbit close to their stars and might be losing their atmospheres, stripped away by intense stellar radiation and wind. These planets are slowly transforming, evaporating, their outer layers boiling off into space over millions of years, potentially leaving behind a rocky core that will become a bare super-Earth once the atmosphere is gone. Astronomers have detected some planets in this transitional state, worlds wrapped in enormous extended atmospheres that stream away from the planet like a comet's tail, gas escaping into space in a slow ongoing process of atmospheric erosion. Now drift with me to the ice giants, worlds similar to Uranus and Neptune in our solar system, composed mostly of water, methane, and ammonia ices surrounding a rocky core, all wrapped in a thick atmosphere of hydrogen and helium. Ice giant exoplanets likely exist in abundance, though they are harder to detect than hot Jupiters or close-orbiting super-Earths because they orbit farther from their stars, take longer to complete their orbits, cause smaller wobbles in their star's motion. But those we have found suggest they are common, representing another large category in the population of worlds that fills the galaxy. An ice giant is not actually icy in the way we usually imagine ice. The interior is hot, heated by the pressure of the layers above and by residual heat from the planet's formation billions of years ago. The ices exist in exotic high-pressure phases, forms of water and methane and ammonia that remain solid or liquid at temperatures that would boil them away at Earth's surface pressure. Deep inside an ice giant, you would find layers of hot compressed ices, perhaps even layers where the pressure is so extreme that methane decomposes into diamond and hydrogen, creating a region where diamonds rain slowly downward through the planet's interior, settling toward the core in a strange crystalline snow. The atmospheres of ice giants are often beautiful, banded with clouds at different altitudes, swept by winds that create long-lasting storms and atmospheric features. Uranus in our solar system has a pale blue-green color from methane in its atmosphere absorbing red light. Neptune appears deeper blue and has faster winds than any other planet in our solar system, with jet streams that reach over 1,000 miles per hour. Ice giant exoplanets likely display similar features, atmospheres layered and structured by temperature gradients and wind patterns lit by the pale light of their distant suns. Some ice giants might orbit at distances where the temperature allows their atmospheres to contain clouds of water ice or ammonia ice, creating weather systems where frozen crystals form and fall through the upper atmosphere, perhaps creating lightning as the ice particles collide and build up electrical charges. Other ice giants farther from their stars would be darker and colder, worlds where the temperature drops so low that nitrogen or even hydrogen might condense, where the atmosphere becomes a thin veil over a frozen landscape of exotic ices. Let us move now to the lava worlds, planets that orbit so close to their stars that their surfaces are molten, covered in oceans of liquid rock that glow with their own heat. These are rocky planets, similar in composition to Earth or Venus, but placed in orbits that bring them so close to their stars that the intense radiation heats their surfaces above the melting point of rock. The day side of such a world might have a surface temperature of 3,000 degrees or more, hot enough that the ground itself is liquid, flowing and churning like water in a pot brought to a vigorous boil. Imagine an ocean of lava stretching to the horizon, glowing orange and red and yellow with heat, releasing shimmering waves of thermal radiation that make the air above waver and distort. The lava ocean is not smooth but chaotic, with currents and flows, areas where cooler, darker crust tries to form only to be broken up and submerged again by the convection of the molten rock below. Bubbles of gas rise through the lava and burst at the surface, releasing plumes of vaporized rock that billow upward into the thin atmosphere. The atmosphere itself on a lava world would be thin and strange, composed partly of rock vapor, minerals that exist as gas in the extreme heat, silicates and metals floating in vapor form around the planet. Some of this vapor might condense at higher, cooler altitudes, forming clouds of tiny rock droplets or mineral crystals that drift through the upper atmosphere before falling back toward the surface where they evaporate again, creating a cycle much like the water cycle on Earth but with rock playing the role of water. On the night side of a tidally locked lava world, the temperature would drop enough for the lava to solidify, forming a crust of cooled rock. But even here the ground would glow dull red with residual heat, and the proximity to the perpetually molten day side would keep the night side much warmer than any night on Earth. The boundary between day and night, the terminator line where the sun sits forever on the horizon, would be a region of constant geological chaos, where rock melts on one side and solidifies on the other, where the surface is caught in an endless transition between solid and liquid. Some rocky exoplanets might be cooler but still volcanically active, worlds covered with active volcanoes that constantly resurface the planet with fresh lava flows. These planets would have landscapes dominated by volcanic features, vast lava plains, towering shield volcanoes, calderas and lava tubes, and fields of solidified lava that stretch for thousands of miles. The atmosphere might be thick with volcanic gases, sulfur dioxide and carbon dioxide, creating a perpetual haze that scatters the light from the star and gives the sky an orange or yellow tint. Now let your thoughts drift to the water worlds, planets where the surface is covered entirely or almost entirely by liquid water, oceans that extend across the whole globe with no continents, no islands, no dry land at all. Earth is sometimes called a water world because oceans cover about 70% of its surface, but a true water world would be even more ocean-dominated. These planets might have formed in the outer regions of their solar systems where water ice was abundant, then migrated inward to warmer orbits where the ice melted, creating global oceans hundreds or even thousands of miles deep. On a water world orbiting in the habitable zone of its star, the surface would be ocean in all directions, waves rolling across the surface driven by winds, tides raised by moons if the planet has any, currents that circle the globe carrying heat from equator to poles. The water might be clear in some regions, murky with life or sediment in others. Beneath the surface, the ocean would extend down into darkness, deeper than any ocean on Earth, eventually reaching pressures so extreme that the water transitions into exotic ice phases that remain solid despite the heat from the planet's interior, forming a mantle of high-pressure ice beneath the liquid ocean above. The sky on a water world might be filled with clouds, water vapor evaporated from the ocean condensing at altitude and forming vast cloud systems that circle the planet. Rain would fall constantly in some regions, feeding back into the ocean below, creating a water cycle of evaporation and precipitation that operates on a planetary scale. The color of the water might vary, blue where it is deep and pure, green or brown where it is shallower or filled with dissolved minerals or organic matter, white where waves break in foam or where the water is covered with floating ice. Some water worlds might orbit farther from their stars, in colder regions where the surface freezes over, creating an ice shell that covers the liquid ocean beneath. These frozen water worlds would resemble larger versions of Europa or Enceladus, moons in our solar system that have subsurface oceans beneath icy crusts. The surface would be frozen, sculpted by ice ridges and cracks where the shell fractures and refreezes, but beneath that frozen surface, perhaps miles or tens of miles down, a dark ocean would persist, warmed by tidal heating or residual heat from the planet's formation, a hidden sea that never sees starlight, where life might exist in the eternal darkness. Among this menagerie of worlds, there are surely planets even stranger, types we have only glimpsed or have not yet discovered, worlds that defy our categories and challenge our understanding. There might be carbon planets, worlds where carbon is more abundant than oxygen, creating chemistry and geology entirely unlike what we see on Earth, with surfaces of graphite or diamond, with mountains of carbon compounds, with atmospheres rich in carbon monoxide and methane. There might be rogue planets, worlds ejected from their solar systems that drift through interstellar space without any star, dark and frozen, illuminated only by the faint glow of distant galaxies. There might be planets and binary star systems, worlds that orbit two suns and experience complex patterns of daylight as their stars rise and set in intricate dances across the sky. There might be pulsar planets, worlds orbiting the ultra-dense remnants of exploded stars, bathed in intense radiation from their strange stellar parents. There might be ocean worlds with hydrogen atmospheres, planets with rings of rock or ice, planets with dozens of moons, planets with days that last for years because they orbit so far from their stars and rotate so slowly. The diversity is staggering, beautiful in its complexity, a reminder that the universe is far more creative than we ever imagined, that planets can exist in configurations and conditions that stretch from the familiar to the utterly alien. Each type of planet represents a different outcome of the planetary formation process, a different roll of the cosmic dice, a different set of initial conditions that led to a unique world with its own character, its own environment, its own story written in rock and gas and ice. As you rest here, as your breathing becomes slower and more regular, as the boundary between waking and sleeping grows softer and less distinct, You can let these images drift through your mind like clouds across the sky, hot Jupiters blazing in the light of nearby stars, super Earths with their heavy gravity and thick atmospheres, ice giants wrapped in layers of compressed water and methane, lava worlds glowing with molten rock, water worlds covered by endless oceans, and all the other strange varieties of planets that fill the galaxy, each one a real place, a physical world, spinning through space under alien skies, shaped by forces both familiar and strange, waiting there in the darkness, part of the great cosmic menagerie of worlds that surrounds us on all sides, scattered among the stars like grains of sand on an infinite beach, each one different, each one remarkable, each one a small miracle of matter and gravity and time. As you settle deeper into comfort, as your muscles release their last holdings of tension, let us drift together toward one of the most profound questions we can ask about these distant worlds, whether any of them might harbor life, whether somewhere among those thousands of exoplanets circling alien suns there might be living things, organisms that breathe and grow and reproduce, that respond to their environments, that exist as we exist, as part of the great community of living matter in the universe. The search for life on exoplanets begins with understanding where life might be possible, which regions around a star offer conditions suitable for living things to emerge and persist. Astronomers call this region the Habitable Zone, sometimes known as the Goldilocks Zone, a band of orbital distances where conditions are not too hot and not too cold but just right for liquid water to exist on a planet's surface. Water is the key, the essential ingredient that defines our concept of habitability. All life on Earth, every organism from the smallest bacterium to the largest whale, requires liquid water to function, to carry out the chemistry of life, to transport nutrients and remove waste, to provide a medium where complex molecules can interact and react. Water is so fundamental to life as we know it that we use its presence or absence as a guide when we search for potentially habitable worlds among the stars. The habitable zone is not a single fixed distance but a range that depends on the star's temperature and brightness. Around a hot bright star like our Sun, the habitable zone lies farther out, perhaps from about 90 million miles to about 150 million miles from the star. Earth orbits at about 93 million miles, placing us comfortably within the Sun's habitable zone, in a location where water can exist as liquid over much of the planet's surface, where temperatures allow for the complexity and diversity of life we see all around us. Around a cooler, dimmer star, a red dwarf perhaps, the habitable zone lies much closer in. These small stars produce less light and heat, so a planet must orbit nearer to receive enough warmth for liquid water. The habitable zone around a red dwarf might extend from only a few million miles to perhaps 15 or 20 million miles from the star, distances that would place a planet inside Mercury's orbit if we were talking about our Sun, but which are just right for the gentle light of a red dwarf. Picture the habitable zone as a softly glowing ring around each star, an invisible shell extending through space, a region where temperatures and conditions favor the possibility of life. Inside this ring, too close to the star, a planet receives too much energy, too much heat. Its water boils away into steam, its atmosphere becomes thick with water vapor that traps even more heat, creating a runaway greenhouse effect that transforms the world into a scorched desert like Venus, where surface temperatures reach 900 degrees and lead would melt into puddles. Outside the habitable zone, too far from the star, a planet receives too little energy. Its water freezes into ice, its atmosphere becomes thin and cold, its surface transforms into a frozen wasteland where temperatures never rise above the freezing point, where any liquid water that might have once existed has long since solidified, locked away in glaciers and ice sheets that cover the planet from pole to pole. But within the Goldilocks zone, at just the right distance, a planet can maintain liquid water on its surface, can have oceans and lakes and rivers, can have weather systems driven by the evaporation and condensation of water, can have climates that vary from warm to cool but never become so extreme that water cannot exist in liquid form somewhere on the planet's surface. Earth demonstrates this balance beautifully. Our planet has ice at the poles where it is coldest, has tropical regions near the equator where it is warmest, and has vast temperate zones in between where liquid water is abundant, where rain falls and rivers flow and oceans lap against countless shores. This range of temperatures, this distribution of water in all its phases, solid, liquid, and gas, creates the conditions where life has flourished, where organisms have adapted to nearly every environment, where complexity and diversity have blossomed over billions of years. When astronomers search for potentially habitable exoplanets, they look first for worlds orbiting within the habitable zones of their stars, planets at the right distance to potentially harbor liquid water. This search has yielded dozens of candidates, worlds that orbit in that special region where conditions might be suitable for life, where the starlight is neither too intense nor too faint, where temperatures might allow water to flow. One of the most famous is Proxima Centauri b, a planet orbiting in the habitable zone of Proxima Centauri, the nearest star to our Sun. This world completes its orbit in just 11 days because Proxima Centauri is a small cool red dwarf and the habitable zone lies very close to the star. Proxima Centauri b likely has a mass similar to Earth's, making it a rocky world rather than a gas giant, and its position in the habitable zone means that liquid water could exist on its surface if the planet has an atmosphere to regulate temperature and distribute heat. We do not know yet if Proxima Centauri b actually has liquid water, do not know if it has an atmosphere or what that atmosphere might contain, do not know if life exists there or ever existed there. The planet is more than 25 trillion miles away, far too distant for our current technology to visit or study in detail. But it orbits in the habitable zone of the nearest star, making it one of the closest worlds where life might potentially exist, a neighboring planet that we might someday explore with robotic probes or study with advanced telescopes that can analyze its atmosphere for signs of biological activity. Another intriguing system is TRAPPIST-1, a cool red dwarf star about 40 light-years from Earth, orbited by 7 known planets, several of which lie within or near the habitable zone. These worlds are roughly Earth-sized, rocky rather than gaseous, packed into a tight orbital configuration where all 7 planets orbit closer to their star than Mercury orbits our Sun. Yet because TRAPPIST-1 is so dim and cool, 3 or perhaps 4 of these planets receive the right amount of starlight to potentially maintain liquid water on their surfaces. Imagine standing on one of the TRAPPIST-1 planets in the habitable zone, looking up at the sky. The star would appear larger than our Sun appears from Earth because you are closer to it, but it would glow with a deep orange-red light, bathing the landscape in colors we rarely see on Earth except at sunset. The other planets in the system would be visible as bright disks in the sky, much larger and closer than any planet appears from Earth, moving visibly across the heavens as they orbit, creating a dynamic sky where planetary transits and alignments would be common, where you could watch neighboring worlds pass in front of each other, where the cosmic dance of the solar system would be immediate and apparent rather than subtle and distant. The surfaces of these planets remain mysterious. We know their sizes and approximate masses, can calculate their densities and determine they are likely rocky worlds rather than gas giants. But we do not yet know if they have atmospheres, do not know if water exists on their surfaces, do not know if their climates are temperate or extreme, calm or violent, suitable for life or utterly barren. Being in the habitable zone is necessary for life as we know it, but it is not sufficient. A planet also needs an atmosphere, a blanket of gas to trap heat and distribute warmth around the globe, to even out temperatures between day and night, between summer and winter, between equator and poles. Without an atmosphere, even a planet in the habitable zone would experience wild temperature swings, scorching heat where the star shines directly in bitter cold in shadows or on the night side. The planet needs a magnetic field too, or at least strong enough atmosphere to shield the surface from harmful radiation. Stars emit not just visible light but ultraviolet radiation, X-rays, and streams of charged particles called stellar wind that can strip away a planet's atmosphere over time if it is not protected. Earth's magnetic field, generated by currents in our planet's molten iron core, deflects most of this solar wind, creates a protective bubble called the magnetosphere that allows our atmosphere to persist, allows water to remain on the surface, allows life to exist without being sterilized by radiation. Red dwarf stars, which are the most common type of star in the galaxy and which host many of the known exoplanets in habitable zones, present particular challenges. These stars are prone to powerful flares, sudden eruptions that blast the surrounding space with intense radiation and energetic particles. A planet orbiting close to a red dwarf, which it must do to be in the habitable zone, would be subjected to these flares regularly, perhaps daily or even more often. Such a planet would need a strong magnetic field or a very thick atmosphere to protect any life on its surface from this harsh radiation environment. Yet life on Earth has proven remarkably resilient, remarkably adaptable. Organisms exist in the most extreme environments our planet offers, in boiling hot springs heated by volcanic activity, in frozen Antarctic valleys where temperatures never rise above freezing, in the deep ocean where sunlight never penetrates and pressures would crush unprotected human bodies instantly, in rocks deep underground where no light reaches and no photosynthesis is possible. Life finds ways to persist, to adapt, to extract energy from chemical reactions or geothermal heat or other sources beyond the familiar sunlight and warmth that support most ecosystems. This resilience suggests that life might be more flexible in its requirements than we initially assumed, that the habitable zone might be broader than our simple calculations based on liquid water suggest, that organisms might exist in environments we would consider marginal or even hostile, clinging to niches where conditions allow for the basic chemistry of life even if those conditions seem extreme by our comfortable standards. Some scientists speak of a habitable zone for complex life versus a habitable zone for any life. Microbial organisms, simple single-celled creatures similar to bacteria or archaea on Earth, might survive in a wider range of conditions than complex multicellular life. A planet at the outer edge of the habitable zone, cold and icy, might still harbor microbial life beneath its frozen surface, in liquid water warmed by geothermal heat from the planet's interior, in subglacial lakes that never see starlight but remain liquid because of the pressure of the ice above and the heat rising from below. A planet at the inner edge of the habitable zone, hot and humid, might have oceans that are bathwater warm, atmospheres thick with water vapor, climates that never experience winter or ice, but which still allow microbial life to flourish in the warm seas, even if complex organisms could not survive the heat and humidity. The search for biosignatures, for chemical signs of life in the atmospheres of distant planets, focuses on gases that might indicate biological activity. On Earth, oxygen makes up about 21% of our atmosphere, almost all of it produced by photosynthetic organisms, plants and algae and cyanobacteria that split water molecules and release oxygen as a waste product. An atmosphere rich in oxygen would be a strong hint that life might exist on an exoplanet, because oxygen is reactive and would not persist in large quantities without something constantly producing it. Other biosignature gases might include methane, which can be produced by certain microorganisms, though it can also be produced by geological processes, making it a less definitive sign. Or phosphine, a gas that might be produced by anaerobic life, life that exists without oxygen. Or combinations of gases that would not naturally coexist unless living things were producing them, like oxygen and methane together, which react to form carbon dioxide and water unless something is constantly replenishing them. Detecting these gases requires analyzing the light that passes through an exoplanet's atmosphere when the planet transits in front of its star. Different molecules absorb light at different wavelengths, creating a unique pattern of absorption lines in the spectrum, a chemical fingerprint that tells us what the atmosphere contains. Future telescopes, more powerful and sensitive than those we have today, will study the atmospheres of potentially habitable exoplanets in detail, looking for these biosignature gases, searching for evidence that life might exist on those distant worlds. The search is patient and methodical, free from urgency or drama. We are not racing against time, not competing against rivals, just slowly building our capability to study these distant worlds in ever greater detail, collecting data, refining our techniques, preparing for the day when we might detect something unusual, some combination of atmospheric gases that cannot be easily explained by geology or chemistry alone that hints at the presence of living things. As you breathe slowly and feel yourself drifting closer to sleep, you can picture this search unfolding across decades, across generations perhaps, astronomers carefully studying one exoplanet after another, measuring their atmospheres, looking for anomalies, for patterns, for signs. Most planets will show nothing unusual, will have atmospheres dominated by nitrogen or carbon dioxide, or hydrogen will show the expected chemistry of a lifeless world shaped only by geology and atmospheric physics. But perhaps one day, on one planet orbiting in the habitable zone of a distant star, the spectrum will show something unexpected. Oxygen in abundance alongside methane, or phosphine in concentrations too high to explain geologically, or some other gas in proportions that suggest biological production, that hint at metabolism and growth and reproduction happening on that faraway world, life whispering across the light years through the chemical composition of its atmosphere, through gases released into alien air by living things we cannot see, cannot visit, can only detect indirectly through their effects on starlight, passing through their world's sky. That discovery, if it comes, would be quiet and careful, edged with caveats and alternative explanations, requiring years of follow-up observations to confirm, to rule out other possibilities, to build confidence that what we are seeing is truly biological rather than some unusual chemistry or geology we have not yet understood. Science moves slowly in matters this important, this profound, requiring multiple lines of evidence, demanding replication, insisting on skepticism until the case becomes overwhelming. But the possibility remains, gentle and persistent, that somewhere in the habitable zone of some distant star, life exists, has emerged from chemistry and complexity, has found its own path through the possibilities that physics and chemistry allow, has created its own forms and functions and ways of persisting, of extracting energy from its environment and using it to grow and reproduce and evolve. Not life like us necessarily, perhaps not even life we would recognize immediately as living, but life nonetheless, matter organized in ways that respond to the environment, that maintain themselves against entropy, that carry information forward through time in patterns of molecules that replicate and vary and adapt. The habitable zone is where we look first, where our search focuses, where the conditions seem most likely to support life as we understand it. But even as we search there, we remain open to surprises, to the possibility that life might exist in places we consider uninhabitable, might find ways to persist in conditions we think too extreme, might be more common or more rare than we expect, might be obvious or subtle, loud or quiet, similar to life on Earth or wonderfully strange. For now, the habitable zones around distant stars remain mysterious, regions of space where water might exist as liquid, where temperatures might be moderate, where the chemistry of life might be possible. We have found dozens of planets in these zones, worlds that orbit at the right distances, that have the right sizes, that might, just might, harbor living things. Each one is a question mark, a possibility, a world waiting to reveal its secrets as our technology improves and our understanding deepens. Rest now, and let your thoughts drift among those distant worlds orbiting in habitable zones, planets where water might flow, where atmospheres might hold gases released by living things, where evolution might be unfolding, where life in whatever form it takes might be looking up at its own alien sky, seeing the stars scattered across the darkness, perhaps wondering as we wonder if other worlds harbor life, if living things exist elsewhere, if the universe is full of whispers that we are only now beginning to learn how to hear, faint and far away but real, signs of life scattered among the habitable zones of distant stars, waiting patiently for us to find them, to recognize them, to know at last that we are not alone. As you lie here in the quiet darkness, your breathing steady and slow, your body heavy with relaxation, I want to guide you through an exploration of numbers, vast numbers that stretch beyond easy comprehension, numbers that speak to the abundance of worlds in our galaxy, the Milky Way. We have discovered more than 5,000 exoplanets so far, confirmed them through careful observation, added them one by one to our growing catalog of known worlds. 5,000 is already a large number, more planets than anyone could visit in a lifetime, more worlds than you could study in years of dedicated attention. But 5,000 is just the beginning, just the smallest fraction of what actually exists out there in the darkness between stars. The true number of exoplanets in our galaxy is not thousands but billions, perhaps hundreds of billions, a population of worlds so vast that it transforms our understanding of what the galaxy is, what it contains, how common planets are in the great structure of stars and gas and dust that spirals through space around us. Let us start with what we know, with the observations that allow us to estimate this enormous population. Astronomers have surveyed thousands of stars, watching them carefully for the signs of orbiting planets, the transits and wobbles that betray the presence of worlds we cannot see directly. From these surveys, particularly from the Kepler Space Telescope, which stared at a single patch of sky containing about 150,000 stars and watched them continuously for years, we have learned something remarkable and beautiful. Most stars have planets. Not some stars. Not many stars. Most stars. Perhaps all stars, or very nearly all. The data suggests that the average star in the galaxy has at least one planet, and many stars have multiple planets, whole families of worlds orbiting in nested rings like the planets in our own solar system. This simple fact, this statistical finding drawn from careful observation, changes everything about how we think of the galaxy. Picture the Milky Way as you might see it on a dark, clear night far from city lights, a band of soft light stretching across the sky, millions of stars too distant to see individually but contributing their combined glow to that luminous river. Our galaxy contains somewhere between 100 billion and 400 billion stars, depending on how you count them, how you account for small dim red dwarfs that are hard to detect and might be more numerous than we realize. The number is uncertain, but it is certainly in the hundreds of billions. If most of those stars have planets, if the average star has 1 or 2 or 3 or more worlds orbiting it, then the number of planets in the galaxy is also in the hundreds of billions. Some estimates suggest 200 billion planets. Others suggest 400 billion or even more. The exact number is less important than the scale, the magnitude, the realization that planets are not rare treasures scattered sparsely through space but common features of the galaxy, present around almost every star, filling the Milky Way with worlds beyond counting. 200 billion planets. Try to hold that number in your mind for a moment, though it will slip away like water through your fingers because numbers this large resist comprehension, refuse to fit into the mental spaces we normally use for counting and estimating. 200 billion is 2 followed by 11 zeros. It is more than the number of stars you could see from Earth even if you had perfect vision and a perfectly dark sky and all the time in the world to look. It is more than the number of humans who have ever lived. It is more than the number of trees in the Amazon rainforest, more than the number of grains of sand on many beaches, more than almost anything you encounter in daily life. If you tried to count to 200 billion, speaking one number per second without pause for sleep or rest or food, it would take you more than 6,000 years. The counting would span all of recorded human history and extend back into prehistory, back beyond the invention of writing, back beyond the first cities, back to when our ancestors were still hunter-gatherers moving across ancient landscapes, and you would still be counting, still working your way through that enormous sequence of numbers. 200 billion planets, each one a place, a physical object spinning through space, following its orbit around a star, shaped by gravity and time and the chemistry of its formation. Some are gas giants larger than Jupiter, enormous spheres of hydrogen and helium massive enough that their own gravity crushes their interiors into exotic forms of matter. Some are rocky worlds like Earth or Mars, smaller and denser, with solid surfaces where geology shapes the landscape, where mountains rise and plains stretch away under alien skies. Some orbit close to their stars, scorched by intense radiation, their surfaces molten or their atmospheres stripped away. Some orbit far out in the cold darkness at the edges of their solar systems, frozen worlds where the starlight is dim and temperatures hover near absolute zero. Some orbit in the habitable zones, at just the right distances where liquid water might exist, where conditions might allow for the chemistry of life. Some orbit in binary star systems, circling 2 suns that will surround each other. Some are rogue planets, ejected from their birth systems, wandering through interstellar space without any star at all. The variety is as staggering as the number. With hundreds of billions of planets, with so many different stars and so many different orbital configurations and so many different formation histories, the galaxy contains examples of almost every possible type of world that physics allows. Hot Jupiters and super-Earths, ice giants and lava worlds, water worlds and desert worlds, planets with thick atmospheres and planets with no atmospheres at all, worlds covered in clouds and worlds where the sky is perpetually clear, planets with moons and planets with rings and planets that tumble through space with chaotic rotations. Consider just the potentially habitable planets, worlds that orbit in the zones around their stars where liquid water could exist on the surface. Astronomers estimate that perhaps 5 to 20% of Sun-like stars have Earth-sized planets in their habitable zones. Even using the conservative estimate of 5%, and even limiting ourselves to stars similar to our Sun, which represent only a fraction of all stars in the galaxy, we arrive at billions of potentially habitable worlds. Not millions. Billions. Let that settle into your awareness as you rest here, as your body grows heavier and your thoughts become softer and less defined. Billions of planets where the conditions might be right for life, where water might flow, where temperatures might be moderate, where atmospheres might shield the surface from radiation, where the chemistry of life might be possible. Billions of worlds that might harbor oceans and clouds and weather, that might see rain fall and rivers flow, that might have day and night cycles and seasons, that might be home to living things, to organisms that breathe and grow and reproduce, that have found their own paths through the possibilities that physics and chemistry allow. We cannot know how many of those billions of potentially habitable planets actually have life, cannot say whether life is common or rare, whether it arises readily wherever conditions permit or requires some additional spark, some unlikely accident that happens only occasionally even given billions of opportunities. But we can say with confidence that the opportunities exist, that the galaxy is rich with worlds where life could emerge, where the basic requirements seem to be met, where the stage is set even if we do not yet know whether the play is being performed. Even if only 1 in a million potentially habitable planets actually develops life, even if the odds are vanishingly small, 1,000,000 to 1 against, there would still be thousands of living worlds in the galaxy, thousands of places where evolution is unfolding, where organisms are adapting to their environments, where the story of life is being written in patterns of molecules and cells and ecosystems. And if life is more common than that, if the odds are more favorable, if life arises wherever it can, then living worlds might number in the millions or billions, scattered throughout the galaxy, closer to us on average than we might imagine. The nearest star system, Alpha Centauri, is about 4 light years away, and we know it has at least 1 planet. The next nearest stars, Barnard Star and Wolf 359, are about 6 light years away, and they likely have planets too, but we have not yet detected them. Within 30 light years of Earth, there are probably hundreds of stars, and if most of those stars have planets, then within 30 light years there might be several hundred planets, perhaps a few dozen inhabitable zones, perhaps a handful where conditions are particularly Earth-like. 30 light years is nothing on the scale of the galaxy, which is about 100,000 light years across. The region within 30 light years of Earth is a tiny sphere, an infinitesimal fraction of the galaxy's volume, like a grain of sand compared to a mountain, like a drop of water compared to an ocean. Yet even that tiny local neighborhood likely contains hundreds of worlds, and as we expand our view outward, the numbers grow rapidly, increasing as we consider larger and larger volumes of space, more and more stars, more and more planets. Within 100 light years, there might be thousands of planets. Within 1,000 light years, millions. Within 10,000 light years, hundreds of millions or billions. And the galaxy extends 100,000 light years from edge to edge, a vast spiral of stars and worlds, all of it filled with planets, all of it hosting these orbiting spheres that we have only recently learned to detect and count and catalog. The distribution is not uniform. Planets are more common around some types of stars than others, more abundant in some regions of the galaxy than in others. The galactic core, where stars are densely packed and radiation levels are high and supernovae are common, might be less hospitable to stable planetary systems than the quieter regions in the spiral arms where our sun orbits. But even accounting for variations in density and habitability, the overall numbers remain enormous, billions of planets spread throughout the galaxy's structure, orbiting stars in the core and the bulge and the spiral arms and the halo. Some of these planets are young, formed only millions of years ago from clouds of gas and dust that recently collapsed to create new stars. Their surfaces are still hot from formation, still being bombarded by leftover debris, still settling into their final configurations. Other planets are ancient, nearly as old as the galaxy itself, formed 12 or 13 billion years ago when the universe was young and the first generation of stars were creating the heavy elements that planets are made from. These ancient worlds have orbited their stars for billions of years, have been eroded by eons of whether they have atmospheres, have been cratered by countless impacts, have perhaps seen life arise and evolve and go extinct, have histories longer than our imaginations can grasp. Every second that passes, as you breathe in and out, as your heartbeat maintains its steady rhythm, these billions of planets continue their orbits, continue their rotations, continue their slow journeys through space. They do not wait for us to discover them, do not pause for our attention, simply exist and move and follow the laws of physics with the same patient inevitability that governs all matter in the universe. On some of those worlds, it is dawn, the local sun rising over the horizon, light spreading across the landscape, warming the surface, driving weather patterns, beginning another day that might last hours or weeks or months depending on the planet's rotation. On others, it is noon, the sun directly overhead, casting short shadows, heating the ground to its daily maximum, driving convection in the atmosphere if the planet has one. On others, it is dusk, the sun setting, colors painting the sky if the atmosphere scatters light as ours does, temperatures beginning to drop as the day side rotates into darkness. On others, it is night, the stars visible overhead if the planet has a clear atmosphere and if there are no clouds, the galaxy itself perhaps visible as a band of light stretching across the sky, other planets in the same solar system shining as bright points or tiny disks, moons rising and setting if the planet has satellites orbiting it. On some worlds, the night never ends, the planet tidally locked with one side always facing away from the star, eternal darkness broken only by starlight and perhaps the glow of neighboring planets or moons. These scenes are happening right now, billions of them simultaneously, each planet experiencing its own local time, its own weather, its own geological activity or stillness, its own patterns of light and shadow. The galaxy is not empty space punctuated by occasional points of light. It is full, densely populated with worlds, a three-dimensional structure where almost every location near a star is also near planets, where the volume of space is subdivided into countless little gravitational wells, each one centered on a star and filled with orbiting spheres, each solar system a miniature cosmos of its own. As you drift closer to sleep, as your conscious thoughts recede and your mind becomes more receptive to images and feelings rather than words and logic, you can let yourself float among this vast population of worlds, not trying to comprehend the numbers intellectually, not trying to count or calculate, just allowing the sense of abundance to wash over you, the knowledge that planets are everywhere, that the galaxy is rich with them beyond measure, that we live in a universe far more generous and creative than we once imagined. Billions upon billions of planets, a phrase that rolls gently through the mind like a wave, like a breath, like a heartbeat. Billions upon billions. More worlds than you could visit even if you traveled at the speed of light for your entire life. More worlds than you could name, more than you could remember, more than you could list if you spent every day from birth to death doing nothing but writing down names and descriptions. The galaxy is a collection of worlds, a vast gathering of spheres, each one following its own path through space, each one shaped by its own history, each one real and physical and present somewhere out there in the darkness. Some are close enough that our fastest spacecraft could reach them in thousands of years. Most are so far away that even traveling at the speed of light would require tens of thousands or hundreds of thousands of years to arrive. But they are all there, all part of the same structure, the same spiral galaxy that we call home, the same immense congregation of stars and gas and dust and planets that wheels through space among billions of other galaxies scattered through the observable universe. You rest on one of these billions of planets, on Earth, a world that orbits a fairly typical star in a fairly typical location in the galaxy, a planet that has liquid water and a protective atmosphere and a magnetic field and all the conditions that allowed life to emerge and evolve and diversify into the millions of species that share this world with you. You are part of the story of one planet among billions, one small chapter in the larger narrative of worlds and life and evolution that might be unfolding in countless places throughout the galaxy. The knowledge of how many planets exist transforms our sense of place, expands our perspective, reminds us that we are not separate from the galaxy but part of it, citizens of a cosmos filled with worlds, inhabitants of a universe where planets are not rare exceptions but common features, where almost every star has its own family of orbiting spheres, where the opportunities for complexity and diversity and perhaps life are repeated billions upon billions of times throughout the structure we call the Milky Way. Rest now, and let the numbers fade into a gentle awareness of abundance, of plenitude, of a galaxy rich with worlds beyond counting, each one spinning silently through space, each one following its ancient orbit, each one part of the vast community of planets that fills the darkness, that makes the galaxy not just a collection of stars but a collection of worlds, billions upon billions of them, more than you can imagine, more than anyone can fully grasp, a multitude of spheres hanging in the void, each one real, each one present, each one contributing to the magnificent totality of planets that surrounds us on all sides, above and below, in every direction, scattered through the thickness of the galaxy like stars themselves, filling the Milky Way with places, with possibilities, with worlds upon worlds upon worlds, billions upon billions, now and forever. As you rest here in the deepening quiet, your body completely relaxed, your breathing slow and effortless, let us look forward together, not with urgency or impatience but with gentle anticipation toward what comes next in our exploration of distant worlds, the new instruments being built, the new methods being refined, the slow patient work of learning to see exoplanets more clearly, to study them in greater detail, to search their atmospheres for the subtle signs that might indicate life exists somewhere beyond Earth. The search for exoplanets has moved through phases, each one building on the last, each one revealing more than we knew before. First came the discovery phase, the 1990s and 2000s, when astronomers found the first exoplanets and confirmed that worlds exist around other stars, that our solar system is not unique, that planets are common throughout the galaxy. Then came the census phase, the cataloging of thousands of exoplanets, the statistical surveys that told us how many worlds exist, what types are most common, where they orbit, how they are distributed among different types of stars. Now we are entering the characterization phase, the detailed study of individual planets, learning not just that they exist but what they are like, what their atmospheres contain, what their surfaces might be, whether conditions there could support life. This phase requires more powerful telescopes, more sensitive instruments, new techniques for extracting information from the faint light that reaches us from these distant worlds. The James Webb Space Telescope, launched in late 2021 and now operating at a point in space about 1 million miles from Earth, represents a major step forward in our ability to study exoplanet atmospheres. Webb is the largest and most powerful space telescope ever built, with a primary mirror more than 21 feet across, covered in gold to reflect infrared light with maximum efficiency. The telescope does not orbit Earth but instead sits at a gravitationally stable location called the second Lagrange point, where it can stare at distant objects without being interrupted by Earth blocking its view. Webb observes primarily in infrared wavelengths, but part of the spectrum where heat radiates, where many molecules absorb light most strongly, where exoplanets are brightest relative to their stars. When an exoplanet transits in front of its star, some of the starlight passes through the planet's atmosphere before reaching us, and molecules in that atmosphere absorb light at specific wavelengths, creating dark lines in the spectrum that tell us what chemicals are present. Webb can detect these absorption lines with unprecedented sensitivity, can identify molecules like water vapor, carbon dioxide, methane, and many others in the atmospheres of exoplanets, can build up a chemical inventory that tells us about the composition and conditions on these distant worlds. In its first years of operation, Webb has already studied dozens of exoplanet atmospheres, finding water on hot Jupiters, detecting carbon dioxide on a gas giant, analyzing the atmospheres of smaller rocky planets to see if they have retained their air or lost it to space. Each observation adds detail to our understanding, fills in another piece of the picture, helps us learn what exoplanet atmospheres are like, how they vary, what processes shape them. The work is meticulous and slow, each target requiring hours or days of observation time, each spectrum requiring careful analysis to extract the subtle signals from the noise, but the results accumulate steadily, building a foundation of knowledge about atmospheric chemistry on worlds beyond our solar system. Picture Webb now, as you lie here on the edge of sleep, a glittering hexagonal mirror floating in the darkness of space, always facing away from the sun, its delicate instruments kept cold in the permanent shadow of its enormous sun shield, staring at distant stars, collecting photons that have traveled for years or decades or centuries across space, sorting those photons by wavelength, measuring them with exquisite precision, sending the data back to Earth where scientists analyze it and learn what it reveals about atmospheres that surround planets no human eye has ever seen directly. Webb will operate for many years, perhaps a decade or more if all goes well, continuing to study exoplanets among its many other scientific targets. But it is designed primarily for other purposes, for studying the early universe and the first galaxies, and while it can characterize exoplanet atmospheres beautifully, it was not optimized specifically for that task. The next generation of telescopes will be designed from the beginning with exoplanets in mind, with instruments and capabilities tailored specifically for finding and studying potentially habitable worlds. One such telescope, still in the planning stages, is sometimes called the Habitable Worlds Observatory, a mission concept that would build a large space telescope specifically designed to study Earth-like planets around Sun-like stars. The telescope would use advanced techniques to block the overwhelming glare of stars, allowing it to directly image planets that would normally be lost in the stellar brightness, to see them as separate points of light, to study their atmospheres by analyzing the light reflected from the planets themselves rather than waiting for transits. Direct imaging is the holy grail of exoplanet observation, the ability to see a planet as a distinct object rather than inferring its presence from shadows and wobbles. It is extraordinarily difficult because planets are so much fainter than their stars, because the contrast is so extreme, because trying to see an Earth-like planet next to its star is like trying to see a firefly hovering next to a searchlight from thousands of miles away. But new technologies are being developed, new methods for suppressing starlight and enhancing planet light, techniques with names like coronagraphs and star shades that can block the light from a star while allowing light from its planets to pass through. A coronagraph is an instrument inside a telescope that creates an artificial eclipse, using precisely shaped masks and mirrors to block the star's light before it reaches the detector, creating a dark region in the center of the image where planets can become visible. Coronagraphs have been used to image giant planets orbiting far from their stars, young worlds that still glow with heat from their formation, but imaging smaller Earth-like planets requires more advanced coronagraphs with better contrast, with the ability to suppress starlight by factors of billions rather than millions. A star shade is an even more ambitious concept, a large spacecraft that would fly in formation with a telescope, positioning itself between the telescope and a target star at precisely the right distance, perhaps tens of thousands of miles away, to cast a shadow that blocks the star's light before it ever enters the telescope. The star shade would be shaped like a flower with petals, designed to create a very deep, very clean shadow, and by blocking the starlight externally before it enters the telescope, it would allow the telescope to see planets that would otherwise be completely lost in the glare. Imagine this for a moment, a delicate flower-shaped spacecraft drifting through space, aligning itself with a distant star, holding its position with exquisite precision while a telescope far behind it peers through its shadow, looking for the faint glimmer of planets, tiny dots of reflected light orbiting the star, worlds made visible by the artificial eclipse created by the star shade's carefully designed petals. The image is peaceful, elegant, a gentle blocking of light that reveals what was hidden, that allows us to see what has always been there but remained invisible because of the overwhelming brightness of the star. These future missions, whether they use coronagraphs or star shades or some combination of technologies, will be able to study Earth-like planets in detail, to measure their sizes and temperatures, to analyze the light reflected from their surfaces and atmospheres, to search for biosignatures, for signs that life might exist on those distant worlds. They will look for oxygen and ozone, for water vapor and methane in combinations that suggest biological production, for the subtle chemical fingerprints that life leaves in an atmosphere through its metabolism and growth. The search will be slow and careful, planet by planet, building up observations over months or years for each target, confirming and reconfirming before drawing conclusions, remaining skeptical and rigorous because the stakes are so high, because claiming to have found evidence of extraterrestrial life requires extraordinary evidence, requires ruling out all other explanations, requires patience and thoroughness and the willingness to question every result until the case becomes overwhelming. Ground-based telescopes are advancing too, growing larger and more capable, developing new technologies to overcome the blurring effects of Earth's atmosphere that have traditionally limited the sharpness of ground-based observations. Adaptive optic systems use deformable mirrors that change shape hundreds or thousands of times per second, compensating for the turbulence in the atmosphere that makes stars twinkle, creating images nearly as sharp as if the telescope were in space. The extremely large telescope, being built in Chile's Atacama Desert, will have a primary mirror more than 100 feet across when it begins operation later this decade, making it the largest optical telescope in the world by far. Its enormous light collecting area will allow it to study faint objects with unprecedented detail, and its advanced adaptive optics will give it the ability to image exoplanets directly, to study their atmospheres, to search for signs of habitability and perhaps life. Picture this massive structure rising from the mountain, a building-sized telescope pointing up at the night sky, its giant mirror composed of hundreds of smaller segments fitted together into a perfect curve, all of them moving slightly and constantly to maintain their shape as the telescope tracks stars across the sky, as adaptive optics compensate for atmospheric turbulence, as photons from distant worlds fall onto detectors and are converted into data, into spectra, into images that reveal worlds that no eye has seen directly. New space missions are planned as well, smaller, faster, cheaper missions that will focus on specific tasks, on surveying particular types of stars for planets, on following up on interesting candidates found by earlier missions, on testing new technologies that will be needed for future flagship telescopes. The European Space Agency's Plato mission will search for Earth-sized planets around Sun-like stars, focusing on finding worlds with orbital periods similar to Earth's one-year orbit, planets that we have not been able to detect easily with previous missions because they require years of continuous observation to see multiple transits. NASA's Nancy Grace Roman Space Telescope, planned for launch in the coming years, will survey a large portion of the galaxy using gravitational microlensing and other techniques to find planets at a wide range of distances from their stars, including planets in wide orbits that are hard to detect with other methods, and free-floating planets that drift through space without any star at all. Roman will also have a coronagraph for testing direct imaging techniques, preparing the way for the more advanced missions that will come after it. These missions represent investments in the future, decisions made now that will yield results years or decades from now, telescopes conceived and designed and built over long timescales, launched when the technology is ready and the funding is available, operated for years or decades if they succeed, gradually accumulating observations that answer questions about planets and stars and the possibility of life beyond Earth. The process cannot be rushed, cannot be forced into schedules that ignore the careful work required to design and build and test instruments that must work perfectly in the harsh environment of space, that must survive launch and deployment, that must operate for years without maintenance or repair, that must achieve sensitivities and precisions that push the limits of what our technology can do. So we wait, and we plan, and we build, and we launch, and we observe, and slowly, patiently, our understanding grows, our catalog of known worlds expands, our ability to study those worlds in detail improves. As you rest here, breathing slowly, your mind drifting through images of telescopes and distant planets, you can feel the gentle rhythm of this process, the long timescale of exploration, the way discovery unfolds not in sudden bursts but through steady accumulation, observation by observation, planet by planet, spectrum by spectrum, each piece of data adding to the whole, each new measurement refining our understanding, each successful mission enabling the next generation of missions that will go further and see more clearly. The search for life on exoplanets is part of this larger rhythm, not separate from it but woven through it, a question that motivates much of the work, that drives the development of new technologies, that gives meaning to the patient observation of distant worlds. We do not know if we will find biosignatures in our lifetimes, do not know if life is common enough and close enough and detectable enough that our instruments will see its chemical traces in some exoplanet's atmosphere, or if life is rare or subtle or difficult to detect, requiring generations of searching before we find it. But the search itself is worthwhile, the slow, patient work of looking, of measuring, of analyzing, of ruling out sterile worlds one by one while remaining alert for the possibility that some world might show something unusual, something that cannot be easily explained except by the presence of living things. Even if we do not find life, we learn about planets, about atmospheres, about the incredible diversity of worlds that exist, about the conditions under which planets form and evolve, about the chemistry and physics that shape these distant places we will likely never visit but can study from afar through the light they reflect or emit. And if we do find life, if some future telescope studying some distant planet's atmosphere detects oxygen and methane coexisting in concentrations that suggest biological production, or phosphine in amounts that cannot be explained geologically, or some other biosignature gas that points toward living things, then everything changes, our perspective shifts again as it shifted when we first discovered exoplanets. And we know at last that life exists beyond Earth, that we are not alone, that living things have emerged somewhere else, have found their own path through chemistry and evolution, have created their own forms and ways of being. That discovery, if it comes, will be announced carefully, hedged with caveats, surrounded by alternative explanations that will need to be ruled out through further observation, through additional years of study, through the slow work of building confidence that what we see is truly biological. There will be no dramatic moment, no single definitive observation, just a gradual accumulation of evidence, a growing consensus that life is the best explanation for what we observe, a gentle dawning of certainty that takes years to develop and must be defended and confirmed and verified before it becomes accepted as truth. But imagine that moment, years or decades from now, when the scientific community reaches that consensus, when the papers are published and the press conference is held and the world learns that we have found evidence of life on another world, that the atmospheres of some planet orbiting some distant star contain gases that indicate the presence of living things, that we are not the only place in the universe where life exists, that the great question that humans have asked for thousands of years, are we alone, has finally been answered, and the answer is no, we are not alone, life exists elsewhere, the universe is richer and more wonderful than we knew. Even then, even with that knowledge, the planets themselves will remain distant, unreachable with our current technology, visible only as points of light or as patterns in spectra, knowable only through the indirect evidence of their atmospheric chemistry, their reflected light, their transits and wobbles. We will not be able to visit them, will not be able to see what life there looks like, will not be able to know if it is simple or complex, microbial or multicellular, intelligent or simple. We will only know that it exists, that living things are there, that metabolism and reproduction are happening on that distant world, that evolution is unfolding, that life has found another foothold in the galaxy. And that will be enough to transform our understanding, enough to answer one of the deepest questions we can ask, enough to change our sense of place in the universe, to know that Earth is not the only living world, that life is possible elsewhere, that the galaxy might be filled with living things on countless worlds, some close, some distant, some simple, some perhaps complex, all of them part of the great community of life that fills the universe, that connects us to processes and patterns larger than ourselves, larger than our planet, larger than we can fully comprehend. As you drift now towards sleep, as these thoughts become softer and more dreamlike, as the boundary between waking and sleeping dissolves, you can carry with you the knowledge that this search continues, that telescopes are being built and planned, that astronomers around the world are working patiently on the instruments and methods that will allow us to study distant planets in ever greater detail, that the quest to find other Earths and to search for signs of life on those distant worlds goes forward, quiet and methodical, driven not by urgency but by curiosity, by the deep human desire to know, to explore, to understand our place in the cosmos. The universe is patient, the planets orbit their stars whether we observe them or not, life exists or does not exist on distant worlds regardless of whether we find it, and our searching is just one small part of the vast unfolding of cosmic time, of stars forming and dying, of galaxies colliding and merging, of planets orbiting and evolving, of time flowing forward second by second, carrying everything along with it, the telescopes and the planets and the light traveling between them, all of it part of one great process, one continuous existence, one universe exploring itself through beings like us who look up at the stars and wonder and build instruments to see farther and ask questions about what is out there in the darkness, waiting to be found. Rest now, let these images fade like stars at dawn, gently and gradually, leaving only peace, only the quiet knowledge that the search continues, that tomorrow's telescopes are being built, that future observations will reveal more, that the quest for other Earths and the search for life goes on, patient and persistent, unfolding across years and decades, a gentle ongoing exploration that connects us to the cosmos, to the billions of planets that orbit distant stars, to the possibility of life scattered throughout the galaxy, to the vast community of worlds that surrounds us, each one real, each one present, each one waiting there in space, orbiting through darkness and light, turning through their days and nights, following their ancient paths around their suns, while we watch from Earth and wonder and search and slowly, patiently, learn what the universe has to teach us about planets and life and the magnificent abundance of worlds that fills the galaxy, the Milky Way, our home among the stars.